Hello there, this is going to be a quick section, Chapter 5, Section 2, which is why it's assigned with Section 3. We're mostly focused on what we hinted at in the last section, which is finding probabilities for normally distributed variables. What does that mean? We're converting regular normal distributions to standard distributions by finding z-scores, then finding probabilities. It's going to feel like we're flip-flopping back and forth quite a bit. Just try to keep your notes straight regarding the mu or mean and sigma or standard deviation of the graph that we're working on, and that will tell you whether we're working with a normal distribution or you're working with one that we've already standardized. Remember, standardizing means that the mean becomes 0 and the standard deviation becomes 1. Okay, if you didn't follow all of that, don't worry about it. Just put a star next to it and ask in class. Pause the video when you need to, rewind the video when you need to. You have control. Okay, let's get the show on the road. Welcome to the lecture video for Chapter 5, Section 2, Finding Probabilities for Normal Distributions. This section is assigned with Section 3 because they are closely related content-wise and they are both rather short. In this section will be understanding how probability is connected to area under the curve when we're talking about the continuous probability distribution called the normal distribution. If a random variable x is normally distributed, we can find the probability of x being within a certain interval by calculating the area under the normal curve for that interval. Let's say that we have a normal curve with a mean of 500 and a standard deviation of 100. To find the probability that our random variable x is less than 600 would be the same thing as finding the area to the left of the value x at 600 under that normal curve. The probability of x being in that interval is the same thing as finding the area that we have shaded in blue there. Why does this work? Let's compare a normal distribution to its associated standard normal distribution with z-scores and a mean of 0 and a standard deviation of 1. So we have this original curve with a mean of 500 and a standard deviation of 100, and we're looking at the probability of a value x being below 600. So if we were using this idea of standardizing the distribution by using the standard formula of z equals x minus mean divided by standard deviation, we would have 600 minus 500, which gives us 100, divided by the standard deviation of 100, which gives us 1. That would mean we have a z-score of 1. When you look at the graph, it matches up with what the graph of the original distribution was. Further, if you think about the fact that we know on a standard normal distribution that the area under the curve is ultimately 1, then finding the area under the curve makes sense in this context. So finding the probability of x occurring below a certain number is the same as finding the area. Finding probability is finding the area. Okay, let's try another example. A national study found that college students with jobs worked an average of 25 hours per week. The standard deviation is 11 hours. A college student with a job is selected at random. Find the probability that the student works for less than 5 hours per week. Assume that the lengths of time college students work are normally distributed and are represented by the variable x. Okay, so we first need to identify that this is normally distributed so we can find the area to solve the probability. Next, we need to see if the values we need are given. They say the mean is 25 hours and the standard deviation is 11 hours. And they want to find the probability that the student works for less than 5 hours per week. So that is our x value. First, let's see what this looks like on a graph. We have a mean of 25, a standard deviation or space between data points of 11, and the x value in question is 5, which is right here. They're wondering what the probability is that the student works for less than 5 hours per week. Okay, so let's find the z-score for our value. We have x, or 5, minus our mu, 25, divided by sigma, our standard deviation of 11. That gives negative 1.82. What does that graph look like? Well, if you draw a standard normal curve, you'd have a mean of 0 and a standard deviation of 1. So negative 2 would be here, and negative 1.82 would be right under it. So we're talking about the same space as the graph above. Okay, so let's figure out the area. You could use the standard normal table or a calculator to find it. If you use the calculator, remember to use the normal CDF function and use a large negative number as your lower bound and negative 1.82 as your upper bound, and 0 as your mean and 1 as your standard deviation. Whichever you use, you should get about 0.0344. This means the probability that the student works for less than 5 hours per week is 0.0344, or 3.34% of college students with jobs worked for less than 5 hours per week. Also, as in most studies, because this amount is less than 5%, it would be considered an unusual event. And what does that mean in this context? It means that most students who have jobs work more than 5 hours per week. Okay, let's try another. A survey indicates that for each trip to a supermarket, a shopper spends an average of 41 minutes with a standard deviation of 12 minutes in the store. The lengths of time spent in the store are normally distributed and are represented by the variable x. A shopper enters the store. Find the probability that the shopper will be in the store for between 20 and 50 minutes. When 200 shoppers enter the store, how many shoppers would you expect to be in the store for between 20 and 50 minutes? Then find the probability that the shopper will be in the store for more than 35 minutes. And then consider, when 200 shoppers enter the store, how many shoppers would you expect to be in the store for more than 35 minutes? Well, let's start with the first part. Let's assume a shopper is in there between 20 and 50 minutes. So we draw our graph first. The average, or mean, amount of time spent in the store is 41 minutes. So that's the amount here in the center. Then the standard deviation, or sigma, is 12 minutes. Okay, the next part is that lower bound of how long people are spending in there is 20 minutes. And the upper bound is 50 minutes. So we set both of those boundaries here. The next step would be to convert both of those boundary markers to z-scores. When we apply the formula to the first or lower bound, we get 20 minus 41 divided by 12, which gives us negative 1.75. When we do 50 minus 41 divided by 12, we get 0.75 for our second boundary. So now our boundaries, formerly 20 to 50, are now negative 1.75 to 0.75. If you remember, the way to find the area, or now we know probability, for this type of problem is to find the area for each with the table and subtract them. You may also remember that you can use your calculator to do this, using both of these values as your lower and upper bounds. So use whichever method you would like here to find the area between these 2 points. And note that you're finding the probability as well. You should get about 0.7333, or about 73%. There is 0.7333 probability that the shopper will be in the store for between 20 and 50 minutes. For the second part of the problem, we need to do another step. It wants to know a proportion of shoppers from 200 that would be there within that range of time. So instead of applying that probability to time, or just giving a percentage chance of something happening, we need to apply it to the 200 shoppers. So we need to multiply the 0.7333 by 200, and we get about 146.66, or 147 shoppers. So we can conclude that when 200 shoppers enter the store, you would expect about 147 shoppers to be in the store between 20 and 50 minutes. So now we can move on to the second question. It asked about the probability of a shopper being in the store more than 35 minutes. So first we look at the graph. Our mu is still 41 and our sigma is 12. This time our x is 35, a little below mu. And this time we are asking about something more than x, so it's a greater than, so we are shading to the right. So we first want to convert 35, our x value, to a z-score. So 35 minus 41 divided by 12 is negative 0.5. Because it's a greater than z problem, we can either subtract the area we find in the standard normal table from 1, or we can use the negative 0.5 as the lower bound and a very high number as the upper bound and use the calculator to find our area. Either way, we should get about 0.6915, or about 69%. This means there is a 0.6915 probability that the shopper will be in the store for more than 35 minutes. What about the second part of the problem? When 200 shoppers enter, how many shoppers can we expect to be in the store for more than 35 minutes? Well, same as the last time, we can just multiply our result, 0.6915, by the 200. We get about 138.3, or 138 shoppers. Now pay attention to this, we round it because you wouldn't have 0.3 shoppers, right? Make sure your answers make sense. That's one of the things we lose when we get in the weeds with these complex problems. Make sure you're popping up every once in a while and thinking, does this make sense? Is this logical? Yes? Okay, good. Carry on. Just every once in a while, check yourself. Okay, let's do one more with our calculators. The very cool thing about your calculator is that it can do these problems without having to change anything that you've learned before. Remember the normal CDF function that you learned last section? You get to use that one again, even without converting to z-scores. Yes, you can actually enter these without converting z-scores first. Let's do this one. In the United States, the number of physicians involved in patient care per state are normally distributed with a mean of 280 physicians per 100,000 resident population and a standard deviation of 78 physicians per 100,000 resident population. You randomly select a state. What is the probability that the state has fewer than 300 physicians per 100,000 resident population? Use technology to find the probability. Use the normal CDF function with the given x value without standardizing to z-scores, so you must use the original mean and standard deviation. So here's a reminder of how to use this function on your TI-84. You want to press the second button, then vars to access the distribution menu, then arrow down to the number 2, normal CDF, not the PDF function, CDF. If you need a large lower or upper bound for a problem, remember the way to enter a lower one is to use the negative button, then 1, then the second button, then the comma, which is selecting the inner exponent or EE choice. You see that above your comma. Then 99, and that's essentially putting a very large negative number in. When you need a very large number, a positive one for the upper bound, just don't use the negative button, but use the rest of those instructions. Okay, for this problem, our mean is 280, our standard deviation is 78, and they want the probability of x being smaller than 300. So we need to enter it this way. We want to do second vars to get the distribution menu, then arrow down to 2 normal CDF, and we want a large lower bound. So we want to do the negative sign, 1, the second button, a comma, that's to get the inner exponent, the EE, then 99, then enter. Now we're doing our upper bound, and you may have a calculator where you have to do commas instead of enter in between these. So if you do that, just know that you need to do commas instead of enter, and when you're finished, you'll need to close your parentheses. Okay, the next entry is your upper bound, that's 300, that's the point that we're looking at, and then enter, or comma, and then our mean is 280, and then enter or comma, and then our sigma, or standard deviation, is 78, and then you enter as many times as you need to for it to calculate. And you should have gotten about 0.601. If you did not get that, rewind this and see if you got any of those steps out of order, or maybe you didn't put a comma in the right place, or you just may not understand the process. Please put a star next to it and ask a question in class. I want to make sure you understand. Okay, so how do we interpret this? That means that the probability that the state has fewer than 300 physicians per 100,000 resident population is about 60.1%. Okay, that may not be something to celebrate, but the fact that you're finished with this section is. Great job. You have finished. So take a break. You deserve it. then get back to section 5.3. Those lecture notes are meant to be done together, but for now, take a breather. Good work. I'll talk to you in the next video.